Hello. Oh, great. Get started. Hello, everyone. Good afternoon in Brazil and good evening in UK. Welcome, everybody, to this special day for me, of course, because I'm having the pleasure and honor to know I can see a special guy, very polite and receptive with me. And thank you very much, Dr. Tindell, to accept my invitation for this special event. And I don't have words to express my happiness. How are you, guy? Are you okay?
Yep, good.
Okay, you are welcome, of course. And this is a special day, as I mentioned before. And we will have this model of presentation, 5 minutes of self-introduction. And after we will have the presentation of the title about Dr. Chino will present. And after we will open to audience to do questions. Okay, you stay free. Feel free to ask questions to that you demand. So our special guest that is attended this Q&A-30 edition is Dr. Ken Tindell. He is the CEO from Canhg Automotive Labs, and the title of the presentation is about the securing CAN bus augmented the CAN protocol. Dr. Cantino is considered as an important guy that made a huge contribution to the automotive sector. He is currently CTO at CAN's Automotive Labs. He has involved with CAN since the mid of 19th, and has extensive experience in the automotive industry. He co-founded Live Devices, a startup that later was acquired by Bosch. He co-founded the Vulcan communication technology, later acquired by Metro Graphics. He has a PhD in real-time systems uh, by University of York. He produced the first time analysis for CAN bus, and also originated the concept of holistic scheduling and to track in the code dependency between CPU and the bus scheduling. He worked with Volvo Cars on the CAN network in the P2X platform and was one of the team that in 1999 won the Volvo Technology Award in car network. His focus today as CTO of CAN's lab on the augmented CAN for both performance and security with the new CAN 8G protocol, upgrading CAN for today's challenges. Okay, Mr. Quintindo, you are welcome. Uh,
Yeah.
you are welcome to do a self introduction, and we can get started your presentation. Right,
Okay.
the work is yours.
Yeah. So you had a bit of background there. So I've been around in this industry for a long time. I started with in the real time systems research group at York, doing timing analysis for CAN bus. Today, that timing analysis is used by a large number of companies, not as much as it should be. But with that analysis, you can guarantee all the latencies on CAN bus, and so it's nice to see that's been used quite a lot. And then I founded Live Devices to work with Volvo on applying that real time analysis. And as you said, that was acquired by Bosch later. And Canis Labs was founded a few years ago now, I think 2016, to address security. And you can see from the structure of the talk I give that we did quite a few things in the security area before we reached what I think is the most appropriate solution for security on CAN. But I thought this talk should talk about these other things because they're still quite commonplace, and give the benefit of what we discovered about things like cryptography and stuff. So this talk will cover in 4 sections. It'll cover attacks on the CAN bus and the kinds of things you can do. Most people don't realize what you can do if you get inside the CAN protocol. I'll cover that in the talk, and I'll give one example of an attack on CAN protocol. There's another video that's got 6 attacks, all in the one video, that shows how you can really screw with the CAN bus. And then I'll talk about intrusion detection, which is the most lame of security techniques, because it doesn't actually do very much. And then we talk about encryption, security gateways, and then finally the most important piece of work that I've been working on for the last few years. So I've moved from doing embedded software to doing chip design, and so this is all done in hardware. So it's been a really interesting project of how to protect CAN bus using hardware directly while still retaining compatibility with CAN. So I hope everyone's going to get something from this, and we'll have a good Q&A at the end.
All right, thank you for a great introduction. Of course, was amazing, and everyone understood everything. Oh, let's get started. Okay. Okay, guys. We'll get start the presentation. After we will be available to questions, asking questions. Okay.
Hi, my name is Dr. Ken Tindell, and I'm the CTO and co-founder of Canis Automotive Labs. I'm here today to talk about how a vehicle's CAN bus is attacked and how to defend it. I'll go over the types of attack, demonstrating them in the lab, and then I'll talk about different techniques for stopping attacks. First, let me introduce myself and Canis Labs. My PhD is in real-time systems, and I created timing analysis to bound the latencies of all frames across a CAN bus. This was deployed first in Volvo cars in the late 90s, and today is fairly widespread. My co-founder is Antal Reinach, an automotive industry veteran and the father of LINBus. We started Canis Labs to focus on technologies to enhance CAN to meet modern challenges, particularly in security. So let's jump straight in and look at attacks on the CAN bus. Conventional attacks on CAN bus are frame attacks. These are where a CAN controller is used to send frames on the bus to disrupt the system. The most common attack is frame spoofing, where a device pretends to be a different one by sending its frames. There are different levels of sophistication in spoof attacks. The most crude level just throws out a frame, but this risks the doom loop, where the spoof and the original are sent at the same time and get stuck in a loop of errors and retransmissions. I have a demo video of the doom loop up on YouTube, so you can see how it plays out. More sophisticated spoof attacks carefully time the spoof frame to avoid the doom loop and exploit how CAN drivers in the receivers are coded. Most reported attacks on CAN bus have been frame attacks, largely because these are the easiest attacks to mount. But there's another set of attacks that aren't well publicized, but are much trickier: CAN protocol attacks. These don't use a CAN controller, they bypass it. These attack the defined behavior of the CAN protocol itself and can do all kinds of nasty things. The attacks work by malware hijacking a device and taking control of the I/O pins that are normally driven by the on-chip CAN controller. These pins are connected to the CAN transceiver and translate digital voltages into differential voltages on the CAN bus wires. The malware can then drive these pins to emulate the CAN protocol, or at least enough of it to trick real CAN hardware into misbehaving in a certain way. As a proof of concept at Canis Labs, we produced the Canhack Toolkit. It's an open source library written in portable embedded C that can run on pretty much any microcontroller. Even a little ARM Cortex-M0 device is fast enough. The library contains a set of functions to mount different types of attacks, and we've wrapped this library up with a CAN MicroPython API so that it can be run from a command line on a tiny Raspberry Pi Pico. Let me show you. This is a Raspberry Pi Pico board. It's a tiny little board sold for $4 and contains an RP2040 microcontroller that has 2 ARM Cortex-M0 CPUs. The Pico is soldered down onto this, a Canhack carrier board. This contains a CAN transceiver wired to a couple of GPIO ports. Custom MicroPython firmware for the Pico contains our Canhack Toolkit so that attacks can be scripted in Python. There are at least half a dozen different low-level CAN protocol attacks discovered so far, and there are higher-level attacks that combine them, I've put up on YouTube a demonstration video that shows 6 different CAN protocol attacks in detail, but I'll demonstrate one here. It's called the Janus Attack. It's a new CAN protocol attack that I conceived recently, and it works by exploiting differences in sample points between different CAN controllers. Let's have a look at some CAN bits. There is usually a bus-wide specification for where the sample point should be. In this example, it's set to 75%. But in practice, inexperienced developers often just set the sample point to 50%. And it's quite common for protocol decoders and logic analyzers to do that too. This generally won't show up as a problem in testing, especially if the CAN bus is short, but this is an opportunity for an attack. By changing the signal level within a bit between 2 different sample points, it's possible to encode different bit values at different receiving CAN controllers. This can be exploited to create a Janus frame, so that it looks like a valid CAN frame at either receiver, but the frames have different payloads. There are some restrictions on forming Janus frames. For example, they have to have the same number of bits, including stuff bits, so they start and finish together. But it's fairly straightforward to find valid Janus frames, and to prove the concept, we created a simple tool to do that. It's released as open source in our Canhack GitHub repository. But to see the attack for real, let's head over to the lab. Here is the benchtop demonstration kit. This is a Raspberry Pi 4. This is a logic analyzer connected via USB to the Raspberry Pi. This is a Canhack board and a Raspberry Pi Pico connected to the Canis Labs CAN Pico board. And here's another CAN Pico board. And the Canis Labs Canhack board has RX and TX pins from the transceiver connected through to the logic analyzer. So the Janus attack is going to attack 2 different receivers. Now we need to set up the CAN controllers slightly differently between them. So the first one will have a sample point of 75%, and the second one will set to 500 kilobits and 50%, which is a common default setting that lots of software and logic analyzers use. And then we will use the CAN Pico library monitor program to display what each of these devices sees. Then we will use Canhack, and we will set 2 frames. The first frame has the CAN ID of 123, and we will have a short payload of 10 hex. And then we'll set the second frame that is going to appear inside the same Janus frame with a slightly different payload, and we mark this as second frame. And we can actually see those frames look like. So we see here the frames have the same number of bits. Now to mount the attack, we need to use the logic analyzer to see what's happened, and we basically send the Janus frame. So if we arm the logic analyzer, send the Janus frame, here we go. So this receiver has received a hex 10 payload, and this receiver has received F4. So 1 frame was sent, and here it's marked as received OK. And the logic analyzer here sees, the decoder sees F4 as the payload, which is this 75%, which is what we set the sample point to. But the other device, because it's got a different sample point, sees a different payload. And we can see the bit stream here is not a regular CAN bit stream for this frame. So if we zoom in a little closer, we can see these strange bit formations here, which are not regular CAN bits. And that's the Canis bit. So this will read 0 in 1, and 1 in a second half, 0 and 1, 0 and 1, and they'll both receive a 1 here. All of them see zeros here, and so on. So we've managed to encode two different payloads inside the one frame by manipulating the Canhg bit sync protocol and by sending a carefully crafted sequence of ones and zeros to the Canhg TX pin, so that we can get two different receivers to see two different payloads. And that's basically the Janus attack. The attacks we've seen are pretty straightforward to carry out. The Canhg protocol attacks in particular just need malware injected into a hijacked CPU, something that's commonly achieved with a buffer overrun attack. And once malware is injected, it's easy to take over the GPIO pins and mount Canhg protocol attacks. So what techniques are there for mitigating these attacks? There are basically four: intrusion detection systems, encryption, security gateways, and new Canhg hardware. None of these techniques on their own prevent all attacks. Protecting a Canhg bus requires defense in depth, and that means multiple overlapping techniques. Let's take a very quick look at intrusion detection. Intrusion detection systems, or IDS, are the CCTV of Canhg bus. They don't actually stop an attack, just observe it happening, and then tell someone about it. Just like CCTV, they will fail to spot every incident, and just like CCTV that triggers when a tree moves in the wind, they'll produce false positives. After something's discovered, the data capture will be reviewed to find out how that happened. A CCTV system based on analog cameras and VHS tape is pretty useless, whereas a UHD 4K video stored on a DVR is a lot more useful. And the same goes for Canhg intrusion detection systems. One built using a regular Canhg controller isn't going to detect Canhg protocol attacks, which are largely invisible, like the Janus attack proves. So a proper Canhg IDS needs to have specially designed Canhg hardware to spot low-level Canhg protocol events. At Canis Labs, we developed our own Canhg silicon IP that can spot protocol attacks. Now let's look at something that can prevent attacks: cryptography. Cryptography can do two things: provide secrecy, where we can't see inside a message, and authentication, being sure about the origin of a message. What it cannot do is provide protection against denial of service attacks. The bus can still be flooded with frames that bring everything to a halt. Authentication is the main purpose of cryptography in an embedded system. It provides a way to know that the message originated from a device and hasn't been tampered with, although we'll see shortly that there are some ways this breaks down. There are two classes of encryption algorithm: symmetric, where all participants share the same private key, kept secret for an observer, and asymmetric, where each device has its own private key and messages to it can be encrypted with its public key. Asymmetric encryption is very slow, even with dedicated hardware. For encrypting traffic on Canhg, we use symmetric encryption. Let's look in more detail at what Canhg requires from cryptography. Canhg was designed around the concept of publish-subscribe. For any given piece of information, there is a single publisher and many subscribers. This is why Canhg frames have a Canhg ID. One purpose of the ID is to identify the information. In fact, in the early days of Canhg, there was a design assumption that one frame would carry one piece of sensor information, which is why Canhg frames can be just 1 or 2 bytes long. The other purpose of the ID is to set the priority of the frame, which is crucial to Canhg's real-time performance. That's a big topic in its own right. The idea is that a publisher device periodically broadcasts a Canhg frame, and subscribers listen for the frame containing the information they need. A subscriber can jump in any time and pick up the latest information. This is important. If a device goes through a watchdog timer restart, it must be up and running quickly. There's simply no time to negotiate a connection to every publisher of information needed and to negotiate keys. This means two things. Firstly, keys must be pre-distributed to all subscribers, and this must be secure. The keys must be kept secret so that software on the device cannot see them. Otherwise, if the device is hijacked by malware, then it can just read the keys out. Secondly, the communication scheme must be random access. There should be no requirement to have all the previous messages received in order to decode the latest one. This sounds obvious, but quite a few encryption schemes only work point-to-point, where both ends have been present from the beginning of a session. That's okay for opening a web page in a browser, but not in a distributed real-time embedded control system. In fact, this is a general problem with trying to adapt mainstream computing solutions. It's a completely different domain, and those solutions often don't work. One final requirement to note, and this goes for any crypto application: don't roll your own. Stick to standards. To quote Bruce Schneier, security has nothing to do with functionality. a cryptography product can function normally and be completely insecure. Flaws remain undiscovered until someone looks for them explicitly. So with all that in mind, let's look at a case study, a scheme for cryptography on Canhg called Cryptocan. Cryptocan is a scheme designed by Janus Labs for communicating in standard Canhg 2.0 frames that provides secrecy and authentication. It uses the standard AES encryption algorithm with 128-bit keys for encryption and the FIPS CMAC algorithm for generating a message authentication code, or MAC. The keys are already pre-shared and stored securely across the devices that need to communicate using Cryptocan. The MAC is calculated on the message payload, which prevents the payload being tampered with, but also on the Canhg ID, which prevents the payload of one message being reattached by an attacker to a different Canhg ID. A freshness value is also included in the MAC calculation, which is provided by the application. This could be a sequence number that is known by the publisher and all the subscribers, or a timestamp kept in sync with a central time broadcaster. Let's see how Cryptocan messages are formed. On the publish side, a plain text Canhg frame plus a freshness value is passed into Cryptocan. The Canhg ID, DLC, payload and freshness value go through the CMAC calculation using a MAC key to create a 60-bit MAC. The Canhg payload, DLC and MAC add up to 128 bits. This makes up an AES block that is encrypted using the cipher feedback or CFB mode. Cipher feedback uses the previous ciphertext and encrypts it. To start the process, a random 128-bit number called an initialization vector, or IV, is used. This is encrypted with the encryption key and then exclusively ORed with the plaintext message block, including that MAC. This creates a ciphertext of 128 bits, or 16 bytes. This is split into two Canhg frames, each with 8-byte payloads. The original Canhg ID is used for the first frame, and the second frame uses the same Canhg ID with one of the bits set to 1, so that the first frame has a higher priority and is sent first. For J1939, this ID encryption bit is the least significant bit of the priority field. The process repeats for each transmission of the Canhg frame, and each time the ciphertext is fed back to generate the next block. On a subscriber side, the reverse operation takes place. The IV doesn't exist for the first message, so the first message received cannot be decrypted. Instead, the ciphertext is used to set the IV, and then the message is discarded. This means with Cryptocan, the first message after a receiver starts is always lost. If this is a problem, for example with sporadic messages that are not repeated periodically, then the message can simply be sent twice. The decrypted MAC is verified by repeating the same calculation as the sender on the same values, payload, DLC, Canhg ID, and freshness value. If the calculated MAC and received MAC match, then the frame is valid and the payload can be used. Cryptocan is designed to be implemented using a hardware security module, or HSM, and in particular, the one designed for automotive applications called Secure Hardware Extensions, SHE. SHE was created some years ago by the German automotive industry, and it's reasonably common in microcontrollers for the industry. It meets the requirements for Canhg encryption we talked about, and implements AES with 128-bit keys and the FIPS CMAC algorithm for message authentication. It also stores keys securely in a walled-off part of non-volatile memory. Keys can be reprogrammed using a secure load key algorithm, using a master key, with new key values encrypted and authenticated in such a way that no eavesdropper can see what the new keys are or tamper with them. SHE can also be used for secure firmware booting. The HSM stores a dedicated boot key and an expected MAC. When a bootloader runs hacked firmware through the HSM with a key, then the calculated MAC will not match the HSM stored MAC, and the bootloader can refuse to run the firmware. An SHE HSM also includes a unique 128-bit factory program serial number and a cryptographically secure pseudo-random number generator, or CSPRNG. And there are permissions that are programmed with each key. Write-only, disabled when the debugger is connected, disabled on boot failure, and whether it's used either for encryption or for calculating a MAC. There are a minimum of 3 and a maximum of 17 user keys in the secure storage for keys. This turns out to be a problem. Any symmetric cryptographic scheme, including Cryptocan, requires a pair of keys, one for authentication and one for encryption. Because SHE specifies only a minimum of 3 user keys, in practice this means that a single bus segment needs to use the same key pair for all encrypted traffic. If there are multiple bus segments and they're to use different keys, then the gateway must use an HSM that has at least a pair per segment and perform decryption and re-encryption as the messages pass through. In this case, messages are not secured end-to-end, and that makes the gateway a particular target for attack, as it's the place that can tamper with messages on the way through. There's another weakness. If a device with an SHE-SHM gets hijacked, then the malware can create CAN spoof frames and ask the HSM to create the authentication code. It can do that for any frame where it has the key that the sender uses. If there's just a single pair of keys for a whole bus segment, then that's any sender. And other devices will accept that spoof frame as legitimate because they will have a valid MAC. This completely undermines the entire point to using cryptography. The SHE Plus specification attempts to address this. SHE Plus adds an extra column in the key permissions table in the HSM. It's for MAC creation. Only the transmitter of the message can be allowed to generate a MAC with that key. Everyone else can only verify a received MAC with the key. This would normally fix the gaping hole, except for the problem of limited keys. Even if the HSM stores the maximum 17 user keys, then this is only a maximum of 16 unique authenticated senders per CAN bus segment. There's a further problem with cryptographic systems: replay attacks. Replay attacks are a problem because an attacker can capture CAN traffic and resend it later. The attacker can easily guess what the message does, and it would be very straightforward to collect a suite of useful messages like unlock the doors or switch off the engine. The receivers will sync to replayed messages, decode and validate them. After all, they were authentic when they were sent, and then use them. The conventional solution to this is to include a sequence number or timestamp, something that changes and can be used to detect stale messages. That's why the AUTOSAR standard calls it a freshness value. Cryptocan includes a freshness value in the MAC calculation. In practice, checking freshness is quite tricky to do reliably. For example, what should the sequence number be if a sender has just reset itself? How do receivers know the number has changed? If there's a message to say sender has reset the freshness value, then what happens if the message is replayed too? Timestamps are also tricky. Every device needs to run on a shared view of time for this to work, and they have to be synchronized by a central clock. What if those broadcasts are replayed? There are solutions to these problems, but they add more complexity and add to the edge cases where the system can fail to communicate. Addressing the security problem creates a reliability problem. Okay, that's enough about encryption. Let's talk about another common way to prevent CAN attacks: CAN security gateways. A security gateway is conceptually very simple. There are two CAN buses. One is the untrusted bus or outside, where we don't trust the environment much, and the other is the trusted bus or inside, where all the devices we most want to protect are. The security gateway sits between the two buses and copies only legitimate CAN frames back and forth. In practice, there are a lot of details to get right, and in any case, gateways don't offer complete protection. For example, authorized messages could be passed through that exploit a remote code execution vulnerability in the firmware of a targeted device. And then we're back to dealing with malware on the trusted CAN bus. This is a particular worry for diagnostics. It's traffic that the gateway has to let through, but a diagnostic stack is a large and complex software stack and consequently has a lot of vulnerabilities. I will talk more about the requirements for a security gateway implementation by using as an example the security gateway developed by Canis Labs. We designed this gateway a few years ago, and it uses a conventional microcontroller with dual CAN bus interfaces interfaced to two different buses. The device also has some local switch inputs. Inside is flash memory that stores rules on what to do with frames. The gateway receives a frame via a CAN controller, and the first thing it does is work out what its logical ID is. This is used to index into the rules table, and the frame's rules are applied. It's then either dropped or forwarded into the outgoing frame queue. The first issue is performance. The gateway must run fast enough to process all possible incoming CAN frames without being overloaded. The smallest time between CAN frames is 47 bit times, or 188 microseconds on a 250 kilobit bus. And there are at least two buses. So the software must be carefully designed to handle this worst case load. The Canis Labs gateway has several different types of rules. There's a basic drop forward rule and a range check rule, which looks at part of the payload to see if it's inside or outside a range of values. This can be particularly useful if the payload contains addresses. There's a real-time rule that puts limits on how often the frame can arrive before it's dropped. This rule is there to prevent flood attacks. It also can handle bursts of frames that are part of a segmented message. There's a final rule, rewriting the CAN frame before it is queued. Parts of the CAN ID in the payload can be changed. One use for this is where a frame on the trusted bus can be exported but with some signal zeroed out to prevent external devices from capturing commercially sensitive information. The Canis Labs gateway can also handle Cryptocan traffic. It can decrypt Cryptocan messages before applying rules, and it can encrypt outgoing messages after applying rules. The gateway also supports multiple modes that enable or disable rules. This is especially useful to stop frames containing OTA firmware until a programming mode is activated, and an interlock can be attached to a mode so that the mode can only be active when a physical input to the gateway is pulled low by a switch. This can be useful where a CAN frame controls some machinery on the trusted side, but must be sent from a user interface on the untrusted side, like a touchscreen on a telematics control unit. Since the interlock is enabled only by a human pressing a physical switch, a compromised device can only activate the machinery when the human is there. The rules table in a Canis Labs gateway is programmed over as CAN bus. It's possible that the only physical access point to the gateway is the untrusted CAN bus, perhaps reached only via diagnostic connector. And so the programming is done by secure messages containing the table, sent using Cryptocan. There is a challenge response protocol used so that the tool and the gateway authenticate each other. The table itself is compiled to binary from a text-based JSON file that describes the rules. The tool protocol is designed to be secure end-to-end, so the tool end may run in cloud infrastructure, with Cryptocan messages tunneled from the infrastructure to the CAN bus. And the programming protocol also includes support for end-of-line provisioning, where the serial number and cryptographic keys are programmed. A secure gateway has to be secure, but must cause as little disruption to the application as possible. One of the most important features of the CAN protocol is its robustness. It implements atomic multicast. Quite simply put, frames are not lost. So when a security gateway receives a frame, then it has to fulfill the same promise. It cannot drop legitimate frames. Keeping this promise comes down to two related things, buffering and jitter. I want to cover the buffering first because this is crucial to the design of a security gateway. The CAN protocol is a priority-based protocol, sending the highest priority, or the lowest ID value, frame first. If there are several frames at any given device, then the highest priority frame inside the device must be entered into CAN bus arbitration. If this isn't done, then we get a horrible problem called priority inversion. In this example, we have three different nodes with queues of frames in FIFO order. The number indicates the CAN ID. The frame we're interested in has ID hex 0F0. It is high priority, the most urgent frame in the system, and normally it would be transmitted first. But just ahead of it in its controller queue is a low priority frame. The three CAN controllers each pick their frame, and then the CAN protocol's arbitration system picks the highest of those. The low priority frame naturally loses to all the medium priority frames. Only when all the medium priority frames have been sent does the lowest priority frame get sent on the CAN bus, and only after that does the urgent frame get to go. In effect, its priority has been inverted. It got treated as the lowest priority frame. Priority inversion is poison for real-time control systems. The most urgent things get stuck and can suddenly experience a huge latency, which has all kinds of knock-on effects. Worse, this is an intermittent problem that might not show up in testing, but happens later in deployment, where the environment is slightly different. That's exactly what happened here in 1997 with the Mars Pathfinder mission, where the spacecraft kept hitting a watchdog timer reset. Fortunately, NASA were able to fix the problem with an OTA firmware update all the way to Mars. What does this mean for a security gateway? Well, the ongoing queues have to be ordered by priority, or specifically CAN IDs. That requires the hardware be capable of internally arbitrating by CAN ID. And it means that the CAN driver software needs to drive the hardware properly. In my experience, that's rarely the case, and lots of systems have priority inversion in the drivers, hidden like a rake in the grass, ready to cause mayhem. I've even seen self-driving car system that sends steering control commands in an urgent CAN frame that could get stuck behind the slowest CAN frame. So if we get the drivers right, that fixes buffering in a security gateway. No, there's still a problem. Some frames must be sent in FIFO order. This is a common requirement for frames in a segmented message, and it shows up a problem with most CAN controller designs. If two frames with the same CAN ID end up in the priority queue, then the hardware makes an arbitrary choice, often reordering frames. which completely breaks segmented messaging. The Canis Lab security gateway addresses this with a rules table. Multiple FIFO queues can be configured and specific frames can be allocated to a specific FIFO. The head of each FIFO then feeds into the main priority queue, so segmented messages can be sent and the system is free of priority inversion. This arrangement isn't perfect. The FIFO frames cannot be sent at full speed. The CAN bus is released while the CAN drivers fetch the next frame from the FIFO, and that lets in a lower priority frame, delaying the next FIFO frame. Fortunately, Canis Labs is designing a new CAN controller based on its CAN hardware IP, and this implements in hardware both priority and FIFO buffering in a single queue stored in the controller, and segmented messages can be sent at full speed. I want to now talk about jitter, because this is an even less appreciated problem than priority inversion. Imagine a regular periodic event that causes a CAN frame to be generated and queued. That queued frame will wait until it is the highest priority on the CAN bus and then be transmitted. The time it waits will be variable though, and sometimes that will be a long time and sometimes small. The arrival time of a periodic CAN frame won't be nice and periodic, it will jitter about. And that's a problem because it means that over a short period of time the frame arrives at a higher rate, which makes the worst case latency of lower priority frames longer, causing knock-on real-time problems. A security gateway makes jitter worse. The outgoing jitter of a frame is inherited from the jitter of the incoming frame, with more added due to variations in processing time within the gateway and then on the bus. If the jitter gets too large, as it almost certainly will when there are multiple gateways in a path, then frames arriving in a receiver can be overwritten by later ones, breaking the atomic multicast promise not to drop frames and damaging the real-time performance of other frames on the bus. There are ways to defeat jitter in a gateway, for example delaying the queuing of a frame if it would otherwise go into the CAN controller too soon. So that's security gateways. They're not perfect, they don't stop hijacking of devices by legitimate traffic, and if not implemented carefully they can cause a system to misbehave by dropping frames and disrupting real-time performance. But there's a role for something that keeps untrusted devices from being electrically connected to a CAN bus. I want to talk now about a new CAN hardware innovation that can provide much of the CAN security discussed so far, but with much less complexity. It's called Canhg and is an augmentation of CAN frames to carry much more data and provide security in hardware. In fact, the H stands for high speed and the G stands for guarded. The way it works is to add out-of-band data into the spare space in a CAN frame. One of the problems of moving to a new CAN bus protocol is compatibility with existing CAN 2.0 devices. For example, if CAN FD frames are sent on a bus segment with original CAN 2.0 hardware, then the hardware sees a CAN FD frame as an error and destroys it. This then means adding bus segments for new and old CAN, leading to more wiring and gateways, which add latency with all the issues of buffering frames and frame jitter. At Canis Labs, we designed a new scheme for augmenting CAN, carrying lots more data, but also retaining backward compatibility with CAN 2.0. We add extra information into a CAN bit where it won't be noticed. In fact, this is like the Janus Attack, by exploiting the CAN protocol sync rules. It works like this. After a 0 bit is sampled, the CAN protocol rules say there is no clock synchronization to edges. As long as we stay out of the window where CAN controllers could sample the line, we can put extra bits in. They will be ignored by existing CAN hardware, but Canhg hardware can extract them. These bits, that we call fast bits, run at 10 megabits a second, and that's on existing wiring with existing CAN transceivers. We've tested this with various wiring topologies with bus lengths exceeding 20 meters and multiple unterminated stubs. There are enough 0 bits in any CAN frame to be able to add 32 fast bits as a Canhg header. This header includes an 8-bit hardware source address, which tags a CAN frame with where it physically came from. That's exactly what we need to spot spoofing. A central intrusion detection system can decode the Canhg header, see a mismatch between where the frame's ID says the frame should come from and where the Canhg header says it did come from, and then know that the frame is a spoof. So, how do the Canhg fast bits get into a CAN frame? Two ways. Either the frame is generated from a Canhg controller, or the fast bits are injected into the CAN signal coming from an existing on-chip CAN controller. This is done with a small Canhg bus guardian chip. It requires only a few thousand logic gates and could even be integrated into a CAN transceiver. Because the central IDS knows for sure if a frame is a spoof, it can take action against it by raising a CAN error, which causes the frame to be destroyed before any CAN controller has received it. The IDS is therefore an IDPS, an intrusion detection and prevention system. It stops a spoof from getting through. In effect, Canhg plus an IDPS provides authentication of a frame, but without any need for encryption. And this protection can apply to devices that don't have Canhg installed. The absence of a Canhg header indicates the frame didn't come from a device augmented with Canhg, which might indicate a spoof. But there's more protection. The bus guardian contains a bus switch that disconnects the host from the CAN transceiver. This is controlled by the IDPS via a command sent over CAN bus with a special command encoded using fast bits. After a spoofing attack is detected, then the IDPS can send a message to the bus guardian hardware to tell it to flip the switch and disconnect the host. This can be used to prevent all kinds of other attacks too. The IDPS can apply rules just like a security gateway does, detecting things like bus flood attacks and directly shutting off the attacker. And inside the bus guardian is a logic block called a PAD, a protocol attack detector, that spots CAN protocol attacks on the CAN TX line and shuts the attacker down automatically. Canhg is useful for more than just security. Although every CAN frame, no matter the size and payload, can get a Canhg header, a CAN frame with lots of CAN 0 bits can carry more fast bits than just a header. A lot more. At a CAN bit rate of 500 kilobits a second, an 8-byte CAN frame takes about 260 microseconds to be sent. But with a CAN payload of all zeros, it has enough room for more than 100 bytes of Canhg augmented payload. At a CAN bit rate of 250 kilobits a second, a carrier frame can hold 250 bytes of payload, all on existing CAN bus wires with existing CAN transceivers, with a classic CAN 2.0 controller hardware attached. This large size of payload means all kinds of new applications are possible. There's also plenty of space to cover the overheads of adding message authentication codes and sequence numbers when using encryption. I realise this sounds a bit like magic, so I will demonstrate it working in the lab. Here are a couple of Canhg development cards we use for testing. Each one contains an FPGA board and a microcontroller board that represents the host. The microcontroller runs MicroPython, which allows us to easily script up tests and demonstrations. The boards are connected together with CAN bus cable. This is a Fleury A cable that's used extensively in automotive. There's also a standard CAN bus connector for other equipment, and here I've attached it to a piece of ribbon cable with a Kvasa Leaf CAN bus tool and a Canis Labs CAN Pico development board with its external CAN controller. There's also a logic analyzer attached that will show precisely what's happening on the CAN bus. One of these Canhg boards will be set up as an IDPS. The intrusion detection chip is created using Canis Labs hardware IP and contains a Canhg engine. A buffer stores incoming CAN frames, and a frame table stores the IDs of up to 256 CAN frames and rules that should apply to each one. It has an SPI interface to a host CPU that can supervise it, and in the demo system the host is an STM32 microcontroller running a special MicroPython firmware build to provide a Python API for the IDPS. In this demonstration there are two senders and an IDPS. The IDPS runs on one Canhg board and has an address of 1. The other Canhg board has an address of 2 and is allowed to send a CAN frame with ID 0x123. The CAN Pico board is allowed to send a CAN frame with ID 0x124. We will see what happens when each board tries to spoof the other's frame. Let's set up the IDPS. We give it a Canhg address of 1 and tell it to automatically block attackers. We tell the IDPS what CAN frames there are. There is a frame with ID 0x123 that comes from address 2. There's also a frame with ID 0x124 that comes from hardware without Canhg augmentation, so it should have no address. We can send a frame from the Canhg board. Let's arm the logic analyzer and send. The busmaster tool has seen the frame. And the logic analyzer shows it has a Canhg header. The IDPS has also received the frame, and it shows it came from address 2. That's all correct. Let's see what happens when the Canhg board tries to spoof frame 124. Let's arm the logic analyzer and press send. We can see the spoof frame got destroyed. Then the IDPS sent a block command and no further attempts to transmit happened because the sender was cut off. The Busmaster tool shows this block command frame, or at least the pure CAN part of it. Let's look at the CAN Pico attempting to spoof a frame. Let's arm the logic analyzer and send. Here we see that the spoof frame didn't get through. It carried on resending until it went bus off. This is because there's no bus guardian hardware on the sender, so nothing to disconnect it from CAN other than the CAN protocol going bus off. And so the block messages are ignored. Without the bus guardian on an attacker, we only do as well as encryption. We can stop an identified spoof, we can't prevent a denial of service attack. Canhg carrier frames can carry much bigger payloads than normal CAN 2.0 frames, and without disrupting existing CAN hardware. I'll show that here. I have a predefined payload of 91 bytes. We can create a CAN frame with that, tagging it as augmented with Canhg. We arm the logic analyzer and send. The frame looks like this on the bus. It's seen as a regular 8-byte CAN frame by classic CAN 2.0 hardware. But at the other Canhg board, it's seen as a Canhg frame with a hardware source address, the sender's timestamp, and a big payload. And here's the payload. So we sent an 8-byte CAN frame that existing CAN hardware saw as a regular CAN frame, but Canhg hardware was able to see as a CAN frame augmented with a large Canhg payload. I'd like to finish by giving a few recommendations for things to do to make life more difficult for attackers and help protect the CAN bus. The first is simple. CAN protocol attacks use direct access to the CAN TX pin, so hide that pin by simply using an external CAN controller. The Janus Attack relies on sample points being set differently at different devices, so another simple thing to do is to check that the sample point is set consistently everywhere. Canis Labs is working on a tool to measure this. Specify that silicon used in control units should include an SHE plus hardware security module. SHE is well designed for automotive use and can be used to prevent tampering with firmware on a device. It also future-proofs devices for adopted encrypted communications. Consider an IDS that can capture high-quality, low-level data for post-incident analysis. Use a properly implemented security gateway to prevent low-trust devices from connecting electrically to a protected CAN bus. And consider using Canhg. Canis Labs IDPS hardware can protect the bus even if not all devices use Canhg hardware. And it can protect your investment in CAN bus by augmenting CAN's capacity to address upcoming needs for years to come. Thank you for watching. You can find out more about these topics from my blog site, kentindell.github.io, and you can contact me by email at ken.tindell@canislabs.com.
Hello, Dr. Ken Tindell. Congratulations. I really appreciate your presentation. It was really amazing. And I'm very excited. This is a unique moment to everyone. Thank you so much again.
Thank you.
So now let's open to the audience to do Q&A, ask questions to you. But I would like to leave this management to my colleague, Dr. Evandro Teixeira. Okay, I'm very grateful for your attention. Hello, Evandro. You are welcome. Evandro? What is, oh, I'm sorry. Oh. Evandro? Just a minute here. Let me check here. Okay, you are welcome. Okay, Evandro, I'd like to give to you permission to manage the Q&A section right now. From now on, okay. Okay, go ahead.
Okay, great.
After the Q&A, we will open the windows to take a picture, right?
Okay, great. So thank you very much, Dr. Tindell. Yeah, so it was a very nice presentation, you know. Actually, we can see that we are in the situation, you know, that we are talking about connected vehicles, you know, so all of this kind of technology. And for me, it's a pleasure because, I mean, I've been working with CAN bus since a long time ago, you know, and I mean, of course, that in the university, we have to show for the students the basic concepts. So all of these technical details that it is related with the CAN bus. And I would like to ask you, you know, why it's important to think about the security in CAN bus, you know, because I mean, I can see that we have, you know, all of this kind of technology, in particular the connectivities in the cars, you know, and I'm sure there is a reason for that. So it should be great if you can explain, you know, for the audience, because some of them, they are not familiar with CAN bus. Thank you.
Yes. So CAN bus is where all the sensors live. It's where all the actuators live, because it's a distributed real-time control network. So if you want to move motors or control engines or apply brakes, it goes over the CAN bus. And CAN was not designed for any security. In '87, I think it was first published. It's 35 years old. And the idea of the internet, I mean, even then you didn't have dial-up internet. So the idea of connecting cars to the internet was absurd. There was no question of it. So nothing in CAN is really thought about. It's as silly as idea as trying to put security on RS-232. It makes, you know, it was absurd at the time. And since then, of course, we've connected lots of things. Now, one of the arguments for security is you don't need to worry about security on CAN because you just protect the perimeter or the outline of the thing, and then nothing can come through that if you firewall the vehicle. Unfortunately, there's lots of bugs in stuff. I mean, I follow the Linux kernel remote coded execution weaknesses, and there are dozens and dozens of these things turning up every year. So you could never secure completely the software of an infotainment system, for example. So therefore you have to put something between the infotainment and the CAN bus because it can go crazy. It has to be connected to the CAN bus because it needs to pick up information like vehicle speed to change the volume of the music playback or something with noise compensation. But you've got to stop it interfering with the CAN bus. And of course, with protocol attacks, it can take control of the pins and do all kinds of evil things. So that's why there's then been this focus on security gateways, which we've had some mixed experience with that. So there have been security gateways themselves that have had vulnerabilities in them. So people have managed to hijack the security gateway from the infotainment side. And then once you get onto CAN bus, you can control pretty much anything that is physically connected by the car. So you could literally crash the car if you were able to spoof things at just the wrong times. Now, some of this is protected by the fact that the cars are safety critical, so they are designed not to fail. But lots of safety engineering, although it's in most languages it's the same word, safety and security. Security is different because in safety you make a probability argument that this should never happen with this probability. With security, there's a human trying to set the probability to 1. So you have to have special techniques above those that you use for safety critical systems. So we need to apply these techniques as soon as we have our vehicles connecting remotely. Now there are some security issues of connecting physically. So you see this in the truck industry where people attach special hacking boxes to eliminate the need for emissions control, and it fakes the sensors and so on. But the biggest risk with passenger cars is the remote connection, and that you can hop from device to device. Once you can break into a device, you can then hop to the next device, and you can make a chain of attacks. So you have to protect the CAN bus. I don't think there's any way to be safe. And if someone manages to find a remote exploit and they were able to attack thousands of vehicles at the same time in an area, this is you could destroy the road network by broken down vehicles. It's not even a case of causing the vehicles to crash. You could just kill the engines on thousands of vehicles all at the same time, and that would just bring all the road network to a halt. And if you start to look at the way we see cyber attacks today, I think this is a big risk. It's cheaper to invest in this than it is to invest in warfare technology. And if you deploy this, you can take out a road without needing to fly airplanes over it and drop bombs. So I think we need to protect Canhg, because and this would go for any control network. It needs specific protections, because that's where all the physical things are attached. And that was a long answer to a short question. Sorry.
Okay, no problem. So actually, I'm asking you. I mean, Max, we need to update our course.
Yes, of course. Yeah. I learn a lot right now.
Yes, it was perfect, your answer, because I mean, this is related with connectivity, because I would say, like, let's say like 5 years ago, we didn't have this in mind that, okay, one day we need to care about it, and of course that we must understand, and we must to show for the people what is the impact about the connectivity. It's not just to to have more more connection with your car, but there is consequence about it.
Yes. It's not just internet connection though. There's other wireless connectivity, Wi-Fi, Bluetooth, even things like tire pressure monitoring sensors. There's no security on those, and you drive past a roadside attacking system that can jump onto them. I mean, we've seen exploits of the tire pressure sensors causing getting access to Canhg by causing an ECU to crash. So yeah, it's short range wireless as well as long range. Yeah.
Okay. Well, I mean, we have more questions here. Okay, I have one question from Andre. Would it be possible to apply any kind of standardization on the safety of the vehicle by the industry? Well, okay. So,
you can read on the chat.
Yes, actually, I'm reading on the chat. Let me, if you
Do
can write in Portuguese, no problem, because I can translate for Tindell. Yeah. Sorry, I didn't understand your question at all. So, sorry, Andre. Okay.
Can you say?
No problem.
Okay, so let's move to another. Mr. Renan, raise his hand. Renan, welcome.
Can you guys hear me? Okay, now. Sorry.
Yes.
It was very nice, your presentation. I loved the insight about the HGCan and introducing the fast bytes. I would like to ask about how the EMC problems would interfere in the fast bits, because sometimes the CAN networks that are already implemented in the vehicles, they go through a lot of EMC, like crazy environments, and would this maybe possibly interfere in this security?
Yeah, so that's a good question. Yeah, so we've tested this on wiring harnesses of different lengths, up to about 25 meters, I think, with lots of stubs and things. And in fact, it's not EMC that's the problem, because the transceivers are actually very good. If you look at the electrical properties of a CAN transceiver, they've got hysteresis and things built in. They're actually extremely good at filtering out noise. So the problem comes with reflections off of unterminated or poorly terminated stubs, where the termination impedance doesn't match the bus impedance, and that causes the reflections. They come through not as noise; they come through as a change in the shape of the bit. So as it goes through the transceiver, effectively, it changes the shape of the bit. And we deal with this in Canhg in two ways. One is we have a filter, a digital filter on the front of the logic block that takes out small glitches that come through the transceiver. And then secondly, we auto-calibrate because the distortions on CAN are mostly down to the physical placement on the wiring harness where the sender and the receiver are physically placed. And if you calibrate for that automatically at the beginning of each frame, because it obviously doesn't change through a frame, then you can work out where the distortions are, and then you can compensate for them, which is why Canhg can run so fast. Sorry, yes.
Very nice, thank you. That's very clever, actually. I love the answer. Thank you, Dr. Tindell.
Any more questions? Okay, Mr. Wellington, please. Would you like to ask for Kindle, or if you prefer to type here?
I can ask.
Okay.
Yeah. So nice to meet you, Dr. Tindell. So I understand that the thinking in a connected vehicle with a switched network with, we have automotive Ethernet in the vehicles nowadays. I also think that protect CAN network is very important because it's the last network until the hacker reach the engine, for example.
Yeah.
So I would like to know the advantage between the CAN AG and the SecOC, for example. I know that SecOC only supports the CAN FD, but and there is no way to implement in classical CAN. But what should be the biggest advantage, for example, for CAN AG?
Right. So the SecOC is basically it's an encryption layer, and it as I went through in the talk, with all the issues that encryption has. So key management. There was I saw a very nice quote which I've now stolen to use, which is encryption is a system for creating a key management problem. That whenever you have encryption, your real problem moves to managing keys, and that's the problem we have with the SHE HSM. There's not enough keys in there to handle that. So as soon as you have that, you have backdoors through the encryption system. So if you manage to hijack an ECU using a buffer overrun or a stack overflow, then you can basically exploit the keys that device has available and then carry on spoofing frames as you would have before. So it actually doesn't solve all the problems. It only solves some very specific problems, and there are weaknesses that you have to work around. So with Canhg, when we built Cryptocan, that's within the SecOp framework. And then we just started to find these problems, these key problems, replay attacks, and so on. And so the reason that Canhg came about was, in fact, we were trying to find a way of securely broadcasting a freshness value that could not be tampered with. So having a device that monitored its own messages and then would see if it was attacked. So Canhg grew out of that, because when we reached the hardware design for that, we thought, well, actually, you could, this actually solves the entire encryption problem we're trying to fix in the first place. So why would you use encryption when you can actually address it in hardware? And by doing it in hardware, this means that every device, regardless of its software or its implementation of software, gets that protection. So the advantage here is there's no replay attack issue, because there's not it's not replaying messages. And you don't have a key problem because you're not using keys, so you don't have a key distribution problem, and you don't have a key database behind it with all the risks of leaking the key database and so on. So eliminating and sidestepping encryption for ordinary message authentication it eliminates all these practical problems, because a lot of encryption is a theoretical problem which you solve with these algorithms, and people can't break them and so on, and you've achieved something, and then you find that actually they just go around the side. So in fact, we've seen this in the internet world with the web. So we built all these certificates for secure website and HTTPS and SSL and TLS and stuff like that. And then what happens? Well, some guy calls up the the certificate issuer pretends to be the customer and gets the key issued to them over the phone because they didn't do any checks. So suddenly your entire cryptography system is collapsed because of some guy answering the telephone in one of the trusted certificate issuers. And so this is the problem with encryption, is it solves a very specific narrow problem, and then all the real problems come around the edges of how you interface that to your real system. So for example, if you look at the SHE system, which is the best hardware security module system I found, it's brilliant. The guys that did that were real experts in cryptography, but in order to change the keys or program the keys into a device, you have to know the master key, and to know the master key you have to have a database somewhere that matches the VIN number or the serial number of the device and the master key. If that database gets leaked, if some guy is bribed some sum of money and he takes it away on a USB stick, the entire protections have gone. So the reason that Canhg was focusing on this and developed is it eliminates all of those key issues and infrastructure issues, because it ties it much more to the physical thing that's there, and that makes it much easier to rely on. And because it's in hardware, you don't need to change your software, you don't need to change the drivers. Everything just fits. Sorry, that's another long answer.
No, not a problem. Yeah, thank you. It was very nice, very clear. And thinking this hardware protection, even automotive Ethernet is going to this way with MACsec, I think. Yeah.
Yes. Well, automotive Ethernet is a bit different because it's a switched architecture, and so you can put, because it's physically switched, you could put quite a bit of security into the switch so that you know which ports an Ethernet source address should come from, and therefore you can actually block it at the switch level. So I think it's a different security problem to CAN because it's not a multi-drop bus. So you can actually do a lot better in hardware on automotive Ethernet too. And I should say that I'm not saying that you don't do encryption. There are roles for encryption. So, for example, if you've got a tool who wants to authenticate to a device in the vehicle and you want to do end-to-end encryption, there's no hardware solution for that. So that has to be done as an encryption solution.
Mm-hmm. Mm-hmm. Perfect. Thank you for your answer.
Okay, that's great. Any more questions? Well, by the way, I would like to thank you for our partners. You know, we have some guys here from the automotive industry, you know, from the Ford and so on. And I would like to thank you for them to come in and discussing, you know, and to see this presentation, because it's very good. Well, I mean, we have one question here from Hannah. Hannah, yeah, please.
Yes. So, hello, Dr. Tindell. Thank you so much for your presentation. Basically, I'm a mechanical engineer, so electronics is not my métier. So I would like to make a really basic question. Considering how it works actually, how the security attacks occurs in the vehicle, is it mandatory to have any kind of connectivity or internet connection in the vehicle, or how it occurs? That's so clear to me.
Yeah. So the threat that we're most worried about is somebody remotely being able to attack a vehicle without physically being there. There are another class of attacks where, say, a burglar wants to steal a vehicle. They can pop the wiring under a wheel arch where the ABS maybe, or find an easy way in. I've seen pictures where they know exactly where the CAN bus is going to be, and they punch a hole in the bodywork and pull the bus cable out, and then you've got a physical attack. So that's a separate set of issues there. But the one that's feared the most is the remote attack, so that you can jump in over the internet, which is the very worst because that can be automated to thousands of vehicles, or you can jump in over Bluetooth connection in the infotainment as a car drives by, or you leave a USB stick maybe lying around somewhere, and then someone plugs that into the infotainment and it hijacks that. So once the software has jumped in onto some complicated device, it can then break through into further into the network. So if you've hijacked the infotainment system in a car, then you could maybe send messages through a security gateway that have got to exploit a bug, say in the diagnostic stack. So lots of the diagnostics for diagnosing mechatronics, you send a command through of multiple frames, and if you send enough and they're deliberately encoded carefully, they can crash the diagnostic software in an ECU that you target, and then the payload of that message contains the malware that then runs in that ECU. Then that ECU is now on the trusted side, and so it can it can take control of the I/O pins that are targeting the connected to the CAN transceiver, and then it can send anything it likes on the CAN bus, and it's got full control at that point. So you can see that it's a chain. You break through the first door, and then the second door, and then you're into your targeted network. And then once you're on the CAN bus, you can send commands that pretend to be from the brakes or pretend to be from the engine, and get all the other devices to act on those. So yeah, it's the remote attacks, I think, is the one that everyone's really frightened of, because you could automate those and run them at a very large scale. So you could attack 1 million cars, break into 10,000 because the conditions are just right, and now you've got a huge attack you can run out. Yeah, so I hope that answers it.
Nice, thank you for your explanation.
Yes. Okay. Thank you. Any more questions? Yeah. Well, I have one question, Dr. Tindell. You know, we are living, you know, we can see that we are living in a world, you know, with a huge transformation, in particular with the Industry 4.0, you know, and also we know that we don't have CAN bus only in the vehicle. So we have this in industry, you know, yep. And yeah. In your opinion, that we should take care about all of these industries, you know, like all of this application. I mean, in terms of security about the CAN bus. Of course, that car, it's let's say it's a very complex, let's say, product, you know, that yes. We have nowadays. Yes. However, we can also have, I mean, I'm just thinking about, for example, when we have, you know, Industry 4.0, and I can connect with my, let's say, with the industry, you know, and take my car and choose the color of my car, something like that, you know. And there they usually also use CAN bus. Do you think that this is a problem, you know, like in a car?
Yes. So yeah, there's a lot of in automation equipment that uses CAN bus. So CAN open is a very common protocol. There are things like elevators and construction equipment. I saw an attack on a crane in a building site where they had a Wi-Fi to CAN bus gateway, and the Wi-Fi was unencrypted and open, and that anyone with a laptop in range of the crane could take control and steer the crane. I mean, that's kind of crazy. So absolutely, is it an issue? And if it's in a factory, and I mean, if you remember the Stuxnet attack on the refinery, the centrifuges in Iran, where they destabilizes the centrifuges, and they blew up the entire plant in the end, and that was using PLCs, standard industry PLCs, and they targeted that through infected USB sticks. If you have a network of industrial machinery connected, yes, the potential for if you find, we see today with the supply chains and how fragile they are. If you target a particular supply chain and a particular manufacturing plant, and you knocked it out in such a way that like in Iran, you caused a fire, or you caused a mechanical failure to cascade. This could have huge effects on the industry, or the world's supply chains. And if that was done in a way as a ransomware attack, and you would said, right, your second factory will be destroyed if you don't give me $1 billion, you can see this is a serious problem. And you know, the fact that it hasn't happened at this level, I don't think is proof that it won't happen. People didn't think Stuxnet was possible. that it was a kind of a Dan Brown novel style of thing, and it's completely possible. And I wonder, in fact, how many ransomware attacks actually have happened, but they've not been publicized because no one really wants to own up to that. So yeah, the industry 4.0 stuff is yeah, and this is why I'm scared of the Internet of Things in the same way. Is this is quite scary stuff, and the Internet of Things is perhaps even worse because the incentives, at least for a manufacturing plant, you have incentives to invest in some security. If it's consumer electronics into homes, nobody cares. The end user doesn't know. The manufacturer has sold the thing and doesn't care anymore what happens. You see this with TVs that don't get updates anymore with security bugs and stuff. So yeah, I think we're in danger of assembling a worldwide infrastructure that could fall apart as soon as someone pushes hard on it, and that's not a good thing to be. Yeah.
Okay. Okay. Thank you very much.
Yeah.
Yes. Max, would you like to ask
For
something?
me, everything is clear because I'm always follow Dr. Ken Tindell through the Canhg's web page, and I had a glad surprise to receive 2 boards from Ken Tindell, and we are using them here. Thank you very much for sending us. Yes. And the opportunity to us train and do tests. And we have a pleasure to receive next year the presentation from Mr. Peter Gliwer from Germany. I forgot to say to him that you could present to us today. I'm so sorry, but I will share with him your presentation. So I'll not take your time anymore because I know that it's a little bit late in UK today, right now. But to keep this moment, I'd like to ask everyone to take a picture, and so everyone could are welcome to open the camera. Okay, Jana. All right, let's go, because I'd like to share this special moment to us. All right, and is it possible to, if someone would like to contact with you, Tindell, is it possible to send an email to you?
Yeah, sure. I think it was on the video. Yeah, sure. And you can find me on LinkedIn as well. That's easy.
Dr. Tindell, my colleague that is Dr. Hiesh, Professor Hiesh, he's the coordinator of the graduate course here in automotive industry. Of course, that we invite you very soon to give a course to us, and feel free to be invited to visit Brazil, of course.
I look out the window, the cold rain and wind here is very much like
yeah.
Max, I'd like to talk about Dr. Tindell. First, thank you for your presentation for my students, and because I have a course of automotive in Brazil, and Max is the professor too.
Okay.
And Valdir Negleri. By the way, I invite you to next year talk about more subjects to us. I appreciate it very, very much. Thank you.
This is a special moment because you receive an invitation to give course in Brazil too. Okay.
Yes.
Be invited. All right. Thank you. I don't know if Jana, did you take a picture? Jana, conseguiu? Jana? Conseguiu. Okay, that's it. Thank you so much for your presentation, your participation.
You're welcome.
I really appreciate it. I'm very excited, and this is a unique moment.